Changing kinetic energy. Energy is conserved. The law of conservation of energy means that energy is never destroyed or created during interactions. The amount of energy in a system is always the same, but it can move from place to place. When energy moves from one place to another, it is called energy transfer. Energy transfer happens when particles collide. Remember, collide means crash. Say a fast moving particle hits a slow moving particle. The slow moving particle speeds up while the fast moving particle slows down. When a particle speeds up, it has more kinetic energy. When a particle slows down, it has less kinetic energy. Energy transfers from a fast-moving particle to a slow-moving particle at the moment of impact. Look at the diagram. So here's what we saw. We saw particle A moving fast, particle B moving slow. They impacted, which means collided or crashed. And then when they move away, they are now moving at the same speed. So what happened was particle A gave particle B some of its energy. Now, at last, they have the same amount of kinetic energy. The total kinetic energy of the two particles before the collision is exactly the same as the total kinetic energy after the collision. No kinetic energy is created or lost as a result of the collision, only transferred. The energy of the two particle system is conserved. But something did change. As a result of the collision, particle A has less kinetic energy and particle B has more kinetic energy. The collision resulted in energy transfer from particle A to particle B. This kind of energy transfer from particle to particle by contact is called conduction. Let's break that down a little bit more. So let's say at first particle A had 4 energy and particle B had 1 energy. When they collide, some of that 4 energy goes to particle B. At the end, there's still the same amount of energy. Maybe now A has 2 energy and B has 3 or 2.5 energy and B has 2.5 energy. So in total, the amount of energy is the same here as here. It's just shared differently between the particles. They now have equal amounts. So this brings up a good question. When the two particles collide, is it possible for the faster moving particle to end up going even faster? Can energy transfer from a low energy particle to a higher energy particle? No, that never happens. Energy always transfers from a fast moving particle to a slower moving particle. As a result of an energy transfer collision, the particle that was going faster before the collision will always be going slower after the collision. And the particle that was going slower before the collision will be going faster after the collision. Always. It is sometimes useful to think of energy as flowing. Energy always flows from higher to lower, from hot to less hot or cold. This word is equilibrium. When you pour cold milk into hot cocoa, the higher energy cocoa particles and lower energy milk particles mix with one another. They collide with each other billions of times every second. The energy flows from the higher energy cocoa particles to the lower energy milk particles. Almost instantly, the average kinetic energy of the milk particles is the same as the average kinetic energy of the cocoa particles. The kinetic energy level is uniform or the same throughout. It is lower than the cocoa and higher than the milk. Has energy transfer between the particles stopped? Not really. Even when the average kinetic energy of the mixture stays steady, some individual particles still have high energy and some particles still have low energy. But the number of high energy particles is the same as the number of low energy particles. When the temperature is constant, the system is in a condition called equilibrium. At equilibrium, temperature does not change. When a mixture of hot cocoa and cold milk has reached equilibrium, you can use a thermometer to measure the equilibrium temperature. The equilibrium temperature is a measure of the average kinetic energy of all the particles in the system. This includes the cup, the mixture of cocoa and milk, and the thermometer. So, has energy stopped flowing? Think about this. The phone rings and you talk to a friend for 20 minutes. Now, the cup of cocoa is cold. Why? The room is cooler than the cocoa. Particles of air collide with the cup and the surface of the cocoa. Energy transfers from the cup of cocoa to the air. Energy continues to transfer to the air until the average kinetic energy of the cocoa is the same as the average kinetic energy of the air. We say the cocoa is room temperature. The cocoa is at equilibrium with everything else in the room.